Bienvenidos, Ushamdi, and welcome to the Chapter 5 and Chapter 6 course lectures. Now, to reinforce what I was stating in the classroom on Wednesday evening, we're going to be flipping the class. In other words, these videos are going to serve as your course lecture. And this also makes sure that both the in-class and online students are going to be benefiting from the course lecture. Typically, only the students who are in the class would get the course lecture. Now, in addition to this, I actually ran a quick pilot on Wednesday evening with an HD camera that I have, as well as a portable microphone. And so I'm actually going to be recording all of the Q&A at the beginning of the class. And I'm also going to be making that video available as well, so that if you wanted to go back and reference that material, you're going to have the opportunity to do so. Now, please don't think that this is going to be a death by PowerPoint engagement. I use the PowerPoint slides as a guide to kind of keep me on track, or these videos may go 7 hours, 8 hours in length. So I'm using the PowerPoints to keep me on track, and yes, I will be referencing what's in the PowerPoints, but we're going to be talking about a lot more than that. So we're actually going to be working with Wireshark. So when we start to talk about the routing protocol, specifically EIGRP, we're going to take a look at something just like this right here, an EIGRP hello packet. We're going to see update packets. We're going to see all kinds of in-the-weeds information about these routing protocols that up until this point, we've really only been theoretically discussing from a textbook perspective. So in addition to PowerPoint, I'm going to be doing a lot of configuration work. As you can see up here, these tabs, I have quite a few routers, a number of them currently offline right now. But we have enough routers so that we're actually going to be able to come up with some pretty interesting use cases. Now, I'm not sure we're going to play this out in its entirety, but this is going to be driving home a number of points. And so this is the topology that we're going to be working with here, where router 2 is connected to router 4, to 5, to 10, 11, 12, and then 15. And again, Wireshark will be capturing each of these segments. Now, I can talk a little bit about how I'm doing that. I'm basically creating what's called a span, or a switch port analyzer port, and then I basically send all of the ports on this switch that I want to see what the traffic looks like. I send that to my span port. I basically monitor the ports that these routers are plugged into, and that's how we're going to be seeing all this information. Now, we'll get busy at times, but I will be sure to slow down and make sure that we take a look at each of these things in turn. Okay, so we're going to cover Chapter 5. We talked a little bit about this, but I wanted to go back through it just one more time. So we talked about dynamic routing. If you remember back to the Routing and Switching Essentials course, in Chapter 2, you talked about static routing. You talked about a next hop static route, right? And let me give you an example of a next hop static route. So if I'm on router 2 here, if I'm in privilege exec, which is the mode I'm in now, and remember, privilege exec is indicated by that pound sign at the end of the host name. If I type in configure terminal, or conf t is really all that needs to be typed in, this puts me into global config mode. So it's from here that I could say IP route, and let's say I wanted to know how to get to the 192.168.1.0, and we'll say it's a /24 to keep it simple. And I know that that happens to be out interface, and this is a fast Ethernet 01, right? Now, this would be a static route. In other words, the way that you would read this is my IP route. So my path to get to this network, the 192.168.1.0/24, is out interface fast Ethernet 01. Now, that would be a directly connected static route where I'm using the outgoing interface. If I wanted to use the next hop IP, right? So in other words, what is the IP address of the router on the other side of that interface, fast Ethernet 01? So when I say fast Ethernet 01, I'm referring to which means this router 2's fast Ethernet 01 interface. When I use the next hop IP address, I'm giving the IP address of the next hop. In other words, I'm giving the IP address of the router on the other side, the interface of the router on the other side. So I would say something like, maybe it's 172. And actually, if I'm on router 2, let's make this a little realistic here. Maybe it's 10.2.4.4. That could be, and if we came over here to router 4, to which router 2 is connected, and I was to go into privilege exec from user exec mode, let me take a step back. So here I am at privilege exec. If I say exit, what's going to happen? Yeah, it logs me off the router. So when I'm here, I'm just kind of a quick sidebar conversation. When I'm here, I'm in user exec mode. When I issue the enable command, this puts me into privilege exec mode. How do I get from privilege exec mode back to, from privilege exec mode back to user exec? Well, we saw that if I type exit, that's not going to work. That's going to log me off, right? So if I'm in user exec and I say enable to get into privilege exec so that I can then go into global config, how do I get from privilege exec back to user exec? Well, the command is disable, right? Enable gets us into privilege exec. Disable is going to take us out of privilege exec, and it's going to put us back into user exec mode. So a little sidebar there. So there's enable, because a lot of students will type exit and then get logged off and not understand, well, why am I being logged off? So if I was to say show IP interface brief, right? I want to see the interfaces that are here, and we can see that between router 2 and router 4, there is the IP address 10.2.4.4 of router 4's interface here. Right now, pay no attention to the fast Ethernet 00.24. This is what's referred to as a sub interface, and we'll get to these at some point in the course. But right now, just kind of go with it and understand that this is an interface, and the IP on that interface is 10.2.4.4. Now, if I come back over here, you can see that's what I'm using as the next hop. So if the 192.168.1.0 network, if I had to get to router 4 to get to that network, then I would have to put this in, right? This static route here, because we're dealing with the static routes. So I would have to put this static route in, and that would help me get to router 4. But the problem is, then when we get to router 4, if I pull the drawing back up, so we put the static route in, let me change my color here to yellow. So I put a static route here on router 2 that says go this way, and let's say that that network, for whatever reason, is way over here, 192.168. I'm probably going to run out of some real estate here, .1.0, and we'll leave it like that. So that's where this network resides. So with static routing, here's what I'm going to have to do. Router 2 is not going to know how to get there. So I have to put a static route in. And then I have to come on to router 4. And I have to put the same static route, but again, I could use a next hop static route with the IP address of that interface, or I could use the directly connected static route with router 4's outgoing interface, or I could use what's called the fully specified static route, which is where I use both of those values. And so we would need another static route here, right? And you can see where this is headed. Another static route here, another static route here, another static route here, another static route here. Now, this takes me one way, right? So this is going to help whatever traffic or the packets, it's going to get them here. The problem is now how do they get back? Because when I issue the ping command here, and I say ping 192.168.1, and we'll just say it's .1 is the IP address that I'm trying to get to over on this segment over here. When I issue this command, what is going to be the source IP address? Yeah, by default with Cisco equipment, the source IP will be the IP of the outgoing interface of the router. And that interface right there is going to be 10.2.4.2. And you can see all of my routers are set up, and I've got these configs or sort of templates that I simply apply to my routers to bring all of these interfaces up. And it will always be the lower router number followed by the higher router number in the second and third octets. They all start with a 10, and then the final octet is the router number, right? So it makes it really easy. So the segment between router 5 and router 10, and again, this is just kind of to familiarize you with what we're going to be looking at here. This the interfaces here are going to be 10.5.10 dot, and I'll put an X here, and this is going to be dot 10, and that's going to be dot 5. So 10.5.10.5 is going to be that interface, and 10.5.10.10 is that interface on router 10. And it makes it very easy to kind of know what the IP addresses are supposed to be instead of using sort of these random values, 172.16.1. It's like, okay, well, where is that segment when we're looking at something like this? So back to the static routing dilemma, right? If it was just 2 routers, that wouldn't be so bad. And that's what a lot of what we learn comes down to. It's going to come down to the use case. What use case are you trying to solve or trying to address? Now, if it was only router 2 and router 4, do I need to run OSPF or do I need to run EIGRP? Probably not, right? If it's one network segment here, right, and let's say there's another network segment that hangs off of router 4 here, maybe it's just static routes is all I need, and that's going to work just fine. Once you start to grow your network out is when you start to see that a dynamic routing protocol is going to be important. And in the context of this discussion, and we have what, 7 routers here. In the context of this discussion, static routing is going to be a nightmare because not only do I have to put a static route on every single one of these 7 routers so that my traffic can get from router 2, right, starting here at router 2, and go all the way to router 15 and beyond router 15, right, because we're trying to get beyond router 15 to that segment, I'm going to need static routes that get me back to the outgoing interface of router 2, the source IP address of what we'll say are these ping packets, right? Now, this is going to be a ton of work, and it's going to get even worse when this happens. Your boss comes to you and says, yeah, we need another network added off of router 2, and that network needs to be able to reach the new network we just put off of router 15. Because now you get to do what I like to call the bonus lab, where you get to now go back and touch every single router individually, adding in additional static routes. And remember, if you wanted a PC, let's say we have a PC here on this whatever this network is here, this new network, and a PC here to communicate, you're going to have to add static routes in all the way this way, and then static routes all the way back in this way. So 2 static routes per router in order to facilitate this new network segment communication between what's beyond router 2 and what's beyond router 15. And so again, I know this, you may be looking at this saying, this is an absurd example. Nobody would ever set this up. And again, we can certainly argue that point. However, it drives home the key takeaway here is that dynamic routing protocols can facilitate these additions and modifications in a dynamic and much faster sense than we ever could do something like this with static routing. Again, static routing is going to require me to touch every single router when something changes, right? A new network segment gets added. And if you see me looking to my left, I apologize. I've got another PC over here that's been crashing lately, and it keeps blue screening on me. So this is where we're at, right? And this is why we use dynamic routing protocols. So again, hopefully you're seeing, I promised I was not going to read the slides, but I will use these slides to kind of stay on track, and we will go through and sort of cover the material that we see in the slides. And so for chapter 5, we had sections 5.1, 5.2, 5.3. We're going to talk about each of those. So there's some key takeaways here. Now, this is a gorgeous slide right here. Absolutely beautiful. Breaks things down for you very simply. When we talk about dynamic routing protocols, there's two classes of dynamic routing protocols. You have your IGPs, and then you have your EGPs. Now, you'll notice I said EGPs with an S. We're going to modify that, right? There is one EGP, and the book did a good job touching on this, right? So when you read the chapter, be sure to focus on the similarities and differences, but the fact that BGP, the Border Gateway Protocol, that is the EGP. There is a single EGP in use on the internet right now, and it is BGP, and that can be a little confusing. So IGPs, right? We've got two subclasses of interior gateway routing protocols. Now you may be asking yourself, well, I don't understand. Why do we have exterior gateway routing protocols? And why do we have interior gateway routing protocols? Why can't we just have everybody run OSPF? Why can't everybody just run BGP everywhere, right? And it's the fact that the routing protocols, they have very different traits and characteristics. The interior gateway routing protocols, those are optimized for convergence and fast convergence. Whereas BGP, and I'm going to refer to it, I'm not going to say EGP anymore, I'm just going to say BGP. And we understand that BGP is the only EGP. So BGP is not optimized for lightning fast convergence and super quick updates, right? BGP is optimized for stability. Again, it's the routing protocol that runs on the internet. So you can imagine what would happen if links are going up and down all around the world. Imagine if it never converged. And we're going to talk about convergence. And what that means is once the routing protocol has settled down and has all the information that it needs in order to function in a continuous state, right? And we'll talk about with EIGRP when routes go active as opposed to being passive. So we've got our distance vector routing protocols and our link state routing protocols under the IGPs. Now, these are markedly different in terms of traits and characteristics. And you can see from the slide, you've got RIP v1 and IGRP. We're not even going to talk about those other than to say you can't configure those or you shouldn't configure those because they are classless. In other words, you can't do variable length subnet masking, a /25, a /26, right? You're not able to do that because the subnet mask is not communicated in the RIP v1 and IGRP updates. They are class full, right? So RIP v1, IGRP are class full, whereas RIP v2 and EIGRP are classless, meaning they don't care about the subnet mask or variable length subnet masking, or the CIDR notation, if you will. They're going to go ahead and they're going to advertise those networks with the subnet mask intact. And then you've got link state routing protocols. Now, they mention ISIS. ISIS, we don't cover that in this class, but it is an extremely powerful interior gateway, link state interior gateway routing protocol. It's used in service provider networks primarily. I'm sure it's used somewhere, someone's got it running for whatever reason, but the value of OSPF and ISIS are that they are link state routing protocols. Again, ISIS is mostly a service provider protocol, whereas OSPF has the overwhelming market share in enterprise networks. Where I work, we run OSPF in multiple locations, many more locations than we do EIGRP. So again, you've got dynamic routing protocols, you've got two classes, IGPs, EGPs. Underneath those, we've got classes of each, right? Under IGPs, distance vector and link state. Under EGP, it's Path Vector Routing Protocol. That's what they refer to BGP as, a Path Vector Routing Protocol. All right. And so this slide just gives you a quick breakdown that inside the little clouds that you see, right, this could be company, let me get my pen up here. So this could be, you know, company A, and yellow is probably not a good color for that. So this could be company A, and this is, you know, this could be Verizon. This is your ISP Verizon. This could be Comcast. And the reason they're showing OSPF in here is because inside the provider network, they could be running OSPF. Inside the provider network, they could be running ISIS. You know, inside company B, they're doing OSPF. Inside company C, they're running RIP. Company A is running EIGRP. Now, here's the major demarcation point, is all of this interior gateway routing protocol information, all of this IGP information. If we want to communicate with Verizon and we want to communicate with Comcast because we're a small to medium-sized company and we have BGP peerings here, right? We would be doing what you learned about back in Routing and Switching Essentials. We would have NAT, Network Address Translation, running here, right? And we could be doing static NAT, we could be doing dynamic NAT, we could be doing dynamic NAT overload, or PAT, which is port address translation. And then we would have communication set up here. But the peering, right? The peering. And what I mean by peering is the communication of this router with Verizon, the communication of our company A router with Comcast. That is being facilitated via BGP. Now, there's a lot more that goes into that conversation with BGP than what I've got here, but this is a great starting point. And you'll notice that this is driving home the point that we've got BGP between the autonomous systems, right? And you don't always have to have BGP, right? It's optional. You could do static routes. And again, it's going to come down to use case. And I love this slide because they took into account something very important here. When you go into your studies, when we get into connecting networks and we're looking at BGP, this conversation is going to come up. I'm a single small company. Let's say this is just company C, right? I'm a tiny little company and I decide that I'm going to peer with what we said was Comcast. I'll just put COM. And it's Comcast. But I only have a single connection to Comcast. That's all we've got because we're a small company. Do I need to run BGP here? Is there any reason for me to run BGP? I could, right? But what if I don't have people that understand BGP well? Maybe I don't want to do it at that point. All I need here for this use case is a static route. And I mean, it's a default static route. You know, your IP route quad 0, and I can use my outgoing interface. I could use the next hop IP address, or I could make it fully specified using both. So we've got a lot of options, okay? And I want you to keep in the back of your mind that word, that phrase I keep using, use case, because that drives, or should be driving, a lot of the decisions that you're making. All right, so distance vector routing protocols, right? And I like how they break the terms down here. Distance is how far. Pretty self-explanatory, right? What is the cost? How long is it going to take me to get there, right? And then the vector is the direction. And that's what distance vector routing protocols are all about. Now, there's a lot of different kinds of, you've got RIP, right? Well, we can break it down. We can say you got RIP v1, RIP v2. Again, RIP v1 is legacy. We've got IGRP, legacy, and then we have EIGRP. Now, we're concerned with RIP version 2 and EIGRP for this course. Those are going to be the two distance vector routing protocols that we're interested in. Now, you'll notice that it doesn't say Cisco proprietary for EIGRP, and that is because if you look up RFC 7868, that is the IETF document that describes the implementation of EIGRP. And so Cisco has now, little by little, started to release the details about how EIGRP should function if another company, like a Juniper, another networking company, decided to make an implementation of EIGRP for their routing operating system. Now, very doubtful that that's going to happen anytime soon, but it has been released. And so they no longer say that it's proprietary. Although it's important to note that there are several features that were not included in the specification. And stub routing, which we will actually discuss, is one of those features. And then you've got a link state routing protocol. And so what is link state routing all about? Well, OSPF and ISIS, those are our link state routing protocols. And the difference between link state and distance vector, and I want you to think of it like this, and I believe the book actually makes this analogy, is a link state routing protocol is like having a map of the entire network, right? Whereas a distance vector routing protocol is more like working with road signs. So, you drive down this country road and you hit the intersection and it says, take a left to get to Route 66. And so that's distance vector. Whereas with OSPF, you have the entire map of the network. So when you set out on that old country road, you already know where you have to go in order to get to 66. It's not that you're waiting to hit the next hop to try to figure out the intersection being the hop. You're not trying to wait till you get to the next hop like distance vector. You already know. You know that you're going down this country road because you have to get to that next hop to get out to Route 66, right? So that's kind of very basic breakdown. So it talked about classful routing protocols, right? And we're not going to be dealing with classful routing protocols, but it's good to know what happens. That they don't support variable length subnet masking. They don't support discontiguous networks. And here's what we mean by discontiguous. Now, if you remember what classful means that 172.16.0.0/16, right? That's a class B, and we should all be very familiar with that. So here's one class B network that's been subnetted. Here's another class B network that's been subnetted. And the problem is that with a classful routing protocol, remember, it doesn't understand what that subnetting means. In fact, it doesn't even communicate that information to the other routers in the routing domain. And we'll assume that this is RIP, I don't think it says, but we'll say it's RIP v1, right? So on router 2, when we configure the route to get to the 172.16.1 and the 172.16.2, it doesn't understand that. It only knows that, hey, 172.16.0.0/16, I can get there this way, and I can get there that way. What's the problem with that? Yeah, how does router 2 know whether it's trying to get to 172.16.2 or 172.16.1? And it doesn't. And you see, as a result, you get that right there. And that's the problem with classful routing protocols, which is, again, why they are obsolete. And you can still configure RIP v1 on Cisco routers. In fact, that's the default. You actually have to put a command in saying version 2 when you create your stanza for router RIP, or else it's RIP v1 by default. Excuse me. And so that's why we no longer do that. IGRP, you can't even configure IGRP on the newer Cisco iOS. In fact, if I was to pull up real briefly, let's bake away from the slides here. So router, where's it at? 10. This is a 3945 router. So this router is even more powerful than the routers that we work on. If I say show version, you'll see here. It's a C3900E. This is a very, very powerful router, and it is running 15.7.3 M3. That is the latest and greatest iOS version for this router, right? So very, very recent version of the iOS. If I go into global config with configure terminal, and I type in router ? Do you see IGRP anywhere? You don't. You see BGP, you see EIGRP, we see ISIS, and remember, it's IS to I, they say IS to IS is how you'll say it, or you'll say ISIS. Do not say ISIS. No one refers to IS to IS as ISIS, right? and not because of the terrorist group. It's never been referred to as ISIS. It's just IS to IS. Intermediate system to intermediate system. And we've got ISO IGRP, which is IGRP for OSI networks, which is not IGRP. Not the IGRP that we're discussing. And then Lisp, and then you see OSPF, V3, and then you see RIP, right? So IGRP is not there. Again, legacy protocol. You've got a nice slide here that talks about, and again, these are generalizations, right? These aren't hard and fast rules. It's not that you can't run EIGRP in a super large network, or that OSPF can't be run in a super small network, right? You can certainly do that. But these are just sort of guidelines more than anything. Now, how do the dynamic routing protocols make their decisions? Well, they make them based off of the metrics that they use to measure what's going on in the network, right? How fast is the link from router 1 to router 2? Is it faster than the link from router 1 to router 3, right? What's the total cost of me to go from point A to point B? And the different routing protocols use different criteria to make that determination. In some cases, and we'll talk about, and I'm talking about primarily the routing protocols that we're going to be using. Let me get a drink of water here real quick. So I'm going to primarily talk about OSPF and EIGRP because that's what we're going to be using. So when we talk about OSPF, OSPF is going to use the interface bandwidth, right? So how fast is the interface will dictate the cost value that OSPF will assign to that interface. And with EIGRP, it's going to be looking at bandwidth of the interface and delay. Now, the EIGRP equation to calculate the metric, to come up with that number, right? Like you can see they have a number here somewhere like a 5 or a 10. Like if the cost was 10, EIGRP has a very scary looking equation that they use, but we're going to be breaking that down and making it very, very simple. In fact, I've written a Python script where you actually plug in the cumulative delay and you plug in the slowest outgoing link speed along the path, and it'll give you the EIGRP metric. And we'll see that as we move along here. And then RIP uses hop count. But again, our focus here is primarily on OSPF and EIGRP. All right, well, that was section 5.1. Let's now dive a little deeper into distance vector dynamic routing, right? Section 5.2. So what we have here is dynamic routing protocols. And again, with distance vector, right, you have RIP version 2 and EIGRP. We're concerned with EIGRP because you'll hear a lot of statements get made about, oh, distance vector routing protocols are susceptible to the count to infinity problem, right? Well, that is something that EIGRP is not susceptible to in terms of issues that the different types of routing protocols can run into. So, operation of a dynamic routing protocol can be described below, and you can see that we're going to be sending updates. And there's a very important description for EIGRP and how it sends its updates. They are partial and bounded. Partial meaning it only sends the update for what has changed. It doesn't send the entire routing table. RIP version 2 will multicast out its entire routing table every 30 seconds. EIGRP, once it has converged, think of it as it's settled down and it's got the information that it needs and there aren't any changes taking place, right? Once it's converged, the only updates that will go out are when something changes, partial. And they'll only go out to the routers that need to get them, bounded, right? And that's a little different than link state, and we'll talk about that when we get to link state. Now, they mentioned this cold start when a router will boot up. it'll go ahead and adds in its directly connected networks. And we saw that over here on router 10. If I say do show IP interface brief, right? So, and actually router 10 does not have, give me 1 second here, and let me see, configure, replace, flash, and sub base CFG. All right, this should do it. I'm pretty sure I've got, show IP interface brief. Let's see if that worked. Okay, that did work. All right, yeah, I only have a single sub interface here. I thought I had all of them. So if I was to say show IP route here, and maybe this is better, you can see that this is that cold start process, right? The router boots up, and hey, look, we have the parent route, and that shows me that classful 10.0.0.0/8, that class A, the parent route, but then it shows me the child, local and connected, right? And here is the connected route. It's a /24. And so the IP address here is 10.0.0.10, right? And I'm actually going to change this. So let's get into global config interface. I apologize here, 00.10, and I want it to be IP address, and actually we want to do incap.1q, whoops, say incap.1q 10, and then IP address 10 dot, oh yeah, that's okay, I'm sorry. So that'll be 10.5.0, and then interface gigabit ethernet 00 dot, we'll say 110, and this is going to be between router 2 and router 10. So we'll do this, and then we'll say incap.1q 210 and IP address. Now, again, you could ignore these commands right here. This is just some cleanup I'm going to do real quickly. 10.2.10.10, because this is a little more advanced the way that I have things configured here. So now if I was to say do show IP interface brief, we should see we have a few more interfaces here. And if I was to try to ping, do ping, remember that do command, do ping 10.2.10.2. So I'm trying to ping router 2 between router 10 and router 2, and let's see if we have connectivity, and we do, right? And so again, do show IP route, you can see that between router 2 and router 10, we have that child network there. Okay, and so then back to tying this into our cold start, this is where the directly connected networks get added into the routing table. Now, excuse me, network discovery with distance vector, right? It's going to be sending updates out. So if we were to take a look real briefly here, I'm going to go ahead and set up EIGRP between router 2 and router 4. So let's go see what that looks like. So here on router 2, I'm going to go ahead and go in from user exec to privilege exec into global config, and I'm going to say router EIGRP 1, right? And this is a little, we haven't talked about chapter 6 yet, but this will be good for you to see how this gets done and then how we configure it. Well, I just need a network statement, right? So I'm going to say network, and the network statement is going to start the EIGRP process on the interface that I indicate here. So I'm going to say network 10 dot, what I say, 2.4 dot, and we'll say 0. And then I put in the wildcard mask. Now, with newer iOS versions, like the versions I'm running, you can say 255.255.255.0. You can put the subnet mask in. Now, when you go to take the CCNA exam, they're going to be looking for that wildcard mask because that typically trips up students. So I'll go ahead and stick with the wildcard mask instead of the subnet mask, right? So that would be 255.255.255.0 for the subnet mask, the wildcard mask being 0.0.0.255, right? So let's pull Wireshark up and let's see, is Wireshark capturing anything? What am I seeing here in terms of these hello messages? And we're looking for, it was router 2 that we set it up on. And take a look, there is a very familiar looking interface number, 10242. So let's take a look here. You can see we've got the layer 1 information, we've got our layer 2 information. Right here is that Cisco, the MAC address from the Cisco router. So how could I confirm this? What if I wanted to tie that back to router 2 to say, hey, is this really router 2? Is router 2 really the source here? So 3 Charlie 18. If I come back to router 2, could I say do show interface fast Ethernet 00 dot, and what do we say? 24, I think, between router 2 and router 4. And there we go. And BIA stands for burned in address. So there's the MAC address. And when I look back at Wireshark, yeah, sure enough, that's it. Okay, so hey, I know that that's the interface that is actually producing this EIGRP hello packet. And that's what dynamic routing protocols do. Like EIGRP and OSPF, they send out hello messages because they're basically multicasting these out. Here's the multicast address, 224.00.10, and they're saying, hey, is anybody else out there on the other end? Hello, does anybody else on this segment want to talk EIGRP with me? I would love to speak EIGRP with you. If you're out there, let me know. And then they would see the hello packets from other EIGRP speakers, which they're about to here in just a second. So again, we've got our layer 3 information. And take a look at the destination address. It's not a unicast packet. If it was unicast, it would be going to the exact router that I'm trying to speak to. This is a multicast packet. Remember, unicast 1-to-1, multicast 1, router 2, to many. It could be one router that I'm trying to get in touch with. It could be 50,000 routers out there on the segment, right? And then you can see here, protocol 88, which is, and actually let me show you that. EIGRP is protocol 88. Here it is. And that is where it's marked in the IP packet that this is an EIGRP packet and that the router should process this with the EIGRP process. And then you peel back that information, and what's encapsulated in this IP packet is this right here. So it's EIGRP version 2. It's a hello message, which is a type 5. We've got some other values that are here, and there's my autonomous system number. I also get my EIGRP version number. And this is actually pretty low. 12.0 is actually a little low compared to the newer iOSs. What about parameters? And we're going to talk about these. There are your K values. Those values that are used to come up with the EIGRP composite metric. And these are multipliers. Remember that. It's not that 0 is off and 1 is the only value to turn it on. 0 means it's not being taken into account. So think of it as off. But it could be 1, it could be 2, it could be 3. It's a multiplier value, so be aware of that. So those are the K values right there. And I'll expand out the software, and you can see we've just got some information about the EIGRP software. And so this is how dynamic routing protocols work, is that they're sending hello packets. So do show IP, oops, sorry, I'm going to say do show IP interface brief. And I want to see, I think it's loopback. Yeah, so each of the routers that we have in our setup, from router 2 all the way to 15, they have a loopback 0 address. And the loopback 0 address, remember, that is a virtual, a logical address. It's not physically on the router, it's just logical, right? And every router's loopback 0 address is the router number for all 4 octets. So router 2 is 2.2.2.2. Router 15 would be, and let's make sure that it's here, and it should be, show IP interface brief, include loopback. Yeah, and loopback on 15 is 15.15.15.15. So again, it makes it easy for our conversation here to sort of follow along with what we're doing. Now, back onto router 2. So we have EIGRP running here. Let's go ahead and start Wireshark again. We'll continue without saving. And we'll start to see all kinds of information. And there's other routers that are out here that are speaking EIGRP. And here's one right here that's doing OSPF. But here's what we're going to do now. We're going to go to router 4. And we're going to jump on router 4. And I'm going to go into privilege exec, into global config with configure terminal. And I'm going to say router EIGRP 1. And that's, remember that 1, the number there is the autonomous system number. And with EIGRP, not OSPF, with EIGRP, the autonomous system numbers must match for the adjacency to form. And the adjacency meaning the bidirectional communication between the 2 routers. So I say router EIGRP1, and then I'm going to add my network statement in for the interface between router 4 and router 2, because now I'm on router 4 side. So I'm going to say 10.2.4.0 and 0.0.0.255. Now I'm going to hit enter, and when I do this, I'm going to quickly move back to Wireshark, because now we're going to see how the adjacency is formed. And take a look. We've got a lot of EIGRP activity here. I'm going to let that go for a second, and then I'm just going to go ahead and swing back. So you can see here that router 2 sends out, router 4 sends a hello packet back out because it saw one from router 2. It's sending these out every 5 seconds. And you can see we even have an ARP request. Take a look at this. Who is 10.2.4.4? So again, remember that 3 Charlie 18? That's router 2. And he's saying, hey, who's 10.2.4.4? Tell me 10.2.4.2, because I want to speak with router 4. We get this EIGRP hello that comes from router 4. And then look at this right here. And we're familiar with the 3 Charlie 18. That's the MAC address on the interface of router 2. And somebody with a MAC address of 2992, with the last 4, responds to router 2 saying, hey, there it is. And so who is it that responded? Yeah, it was router 4 that said, hey, here's my MAC address, right? So there's a great opportunity to take a look at an ARP packet. Wireshark is on the class PCs. It's also free to download, right? So if you wanted to download Wireshark, you can download it and just start capturing packets off an interface and take a look and see what you can see. So now we get into the core of our conversation. A hello packet goes from router 4 to router 2, right? It's an EIGRP packet. And then router 2 sends router 4 an update. And then we get an acknowledgement packet, a hello, and we'll discuss the semantics of the difference between a pure hello packet and just an acknowledgement. Acknowledgement's an empty EIGRP packet. You can see that we don't have, it's not passing any information, right? And that just acknowledges receiving the update, because the update requires an acknowledgement. It is a reliable packet, the update packet, which means it mandates that if I send you, and you can take a look here, how is it sending that packet? Yeah, it's sending it unicast. It's no longer multicast. The update is very specific. Router 2 is sending an update to router 4, and we'll actually take a peek here and see what we've got. It just sends an update to router 4 with information, and when it's unicast and it's a reliable packet type, like an update, it's going to need an acknowledgement to come back. And so here's the information we get. So now let's make this interesting. I want router 4 to know how to get to the loopback address of router 2. Remember that address 2.2.2.2? So let's capture, and we'll see what's going on here. And actually, let me let this run for a few seconds, and you'll see that every 5 seconds, we'll follow router 2. So there's router 2, and that was at, whoops, the time went by pretty quick. We should see every 5 seconds a hello, right? There's a hello from router 2. There's another one, and we've got some other things going on here. So it's a little busy, but let's do this. I'm router 2, and I want to make sure that everybody in my dynamic routing domain, my dynamic EIGRP routing domain, knows how to get to the 2.2.2.2. Again, remember, if this was static routes, I'd have to put one on router 2. I'd have to put one on router 4. I'd have to start putting at least 2, right? One to get where I'm going, and then one to get back. So here's all I need to do. Is I'm going to say network 2.2.2.2 because it's a /32. It's what we call a host route. And in Routing and Switching Essentials, you should have seen some of these, as well as Introduction to Networks when you were working with subnetting. You would have seen things like this. This is referred to as a host route. Host route meaning all of the subnet bits are 1. So it's a /32. All 32 bits of the subnet mask are being used. And so we want to see this because this is going to facilitate an update from EIGRP. So as soon as I hit enter, we work our way back. And whoop, that was pretty quick. Actually, that update, I think, went pretty fast. And there it is right there. Now, the reason I did this is because I want to show you what happens when an update goes out. This is the information that's being shared in the update, right? So you can clearly see router 2, and who does he send the update to? Yeah, he multicasts it out because it's possible that there's 50 routers on this very segment, right? This is a multi-access segment. It's not a point-to-point serial link. So it's possible that there's 50 routers. They're all plugged into like a really big switch. Maybe they're all speaking EIGRP to each other. So he multicasts this out. And what does he get back from router 4? He gets an update. I'm sorry. He gets an acknowledgement to the update, which is simply an empty hello packet, right? You can see here we've got all the flags, and let me make sure we're gonna pause here for a second. So here's a true hello packet. You have the parameters in the software version in a true hello packet. You can see this here, right? Because remember, I'm trying to discover neighbors via multicast. So I want to make sure that the neighbors know, here are my K values, right? These composite metric values, which we're going to talk a little bit more about. And I'm communicating those. How is that different from this acknowledgement packet here? Where's the software version here? It's not here. Where are those K values? Where are the EIGRP parameters? They're not here. Because again, this is what we refer to as an empty hello packet. And so that's the difference. An acknowledgement packet is simply an empty hello packet. Empty because it doesn't have the K values in it, and empty because it doesn't include the software version or any of that other information that we saw in the true hello packet. Now, in some literature, you'll read where they'll say it's an acknowledgement packet, but they make no reference to the hello, that it's just an empty hello packet. So remember that. And I really like how Wireshark has the little ACK out here, right? Telling me, hey, it's a hello packet, but it's an acknowledgement packet, meaning that it's an empty hello packet. No parameters, no software version. It's just simply coming back to say, hey, right, where are we at here? Here's the acknowledgement that I'm interested in here. This is router 4 just saying, hey, I got your update. And here's router 4 sending an update out as well. And take a look at router 4's update. It's updating the fact that it now knows how to get to the 2.2.2.2. And this is distance vector routing, right? Sorry about that, kind of jumping around. And that's distance vector routing. Is router 4 says, oh my God, I now know how to get to this new network. So I need to tell my neighbors, hey, I know how to get to this new network. And it doesn't matter that it learned it from router 2 here, right? It multicasts it back out saying, hey, I know how to get there. Now, router 2, with whom router 4 has an adjacency, router 2 is going to give an update back, right? Or I'm sorry, an acknowledgement packet back saying, yeah, I got your update. And we'll get into the semantics of, yeah, this is the exchange that takes place, but router 2 does not now say in its routing table, oh, if I need to get to the 2.2.2.2, I go to router 4. And then router 4 says, well, yeah, I go to router 2, and then we have a loop, right? So that's not what's happening from a routing table perspective, but from a message perspective, that's what we see here. And again, it's being multicasted out, that 224.00.10. All right, so let me step back to the deck here. And we just saw some update. Again, PowerPoint slides are great as a guide, but I want to get you onto the command line. I want you to see what really is taking place. And so there are the update messages that we just generated, exchanging the routing information. And so now we would say that these routers are fully converged. So if I type in, and if I was to say show IP EIGRP neighbor, right, here is, and I'll move it up a little bit, here is the EIGRP neighbor relationship. Router 2 sees that it has a relationship with router 4. There's the IP address of router 4. This H, it stands for handle, and this is just a numeric representation of when this router learned about this neighbor. So if router 2 had additional adjacencies, you would see 1, 2, 3, 4, and so on. There's the interface out which it learned about router 4. There's your hold time. We'll talk about that in EIGRP. 9 minutes, 13 seconds. That's how long router 2, this adjacency, has been up. Smooth round trip time, we'll get into a little bit more. Same with RTO. Queue count should always be 0. If you see queue count incrementing, like 1, 2, 50, 80, you have a problem. And then the sequence number. Again, we'll talk about these more in depth so when we get to EIGRP. So those are a lot of the values that we are seeing. Now, split horizon prevents information from being sent out the same interface from which it was received, right? This is a distance vector trait. Now, what EIGRP uses is split horizon, which means if I get an update, and let me get the pin up here. So from router 1's perspective here, let's say that an update comes in from router 2, right? Split horizon prevents information from being sent out the interface on which it was received. Well, what did we just see? We just saw that an update was multicasted out the same interface. So what we say is split horizon would be the update comes in, and then router 1 says, well, I learned the update in this instance from router 2. I'm not going to send it back out the serial interface because that's the same interface on which I learned it. Now, this is a point-to-point link. It is not a multi-access segment, and these behave differently. EIGRP can use what's called split horizon, which means it won't send it back out, with poison reverse, right? And poison reverse means that the interface on which it did learn about it, it would send it back out with a metric of infinity, right? Meaning unreachable. Now, when RIP does this, it sends it out with a hop count of 16. Because remember, the maximum hop count is 15. So RIP would send it out with a hop count of 16, meaning router 2 would be like, oh, well, I can't get to that. I'm not going to install that into my routing table because I can't get there. It's got a metric of 16. And EIGRP does something very, very similar. And again, we'll dig into that. But remember, split horizon means if I get an update on an interface, right? If I receive routing information on an interface, I'm not going to advertise that information right back out the same interface. That doesn't make any sense. Because if router 2 told me, here's how you get to the 10.4.0.0 network, I don't need to tell router 2 how to get there because router 2 is the one telling me, right? And that is split horizon. Poison reverse means that when I do send it back out, if that's how the distance vector protocol is behaving, like RIP v2, if I do send it back out, I'm going to send it back out to that specific router on a point-to-point link with a metric of infinity, right? Remember, it's a little different on the multi-access segments. Okay, convergence time. You can read this. Remember, it's the time it takes the routers to all settle down when there are no changes being made. Because eventually your network is going to, your networks are 99.9% of the time, they're converged. Right? It's not an every hour, it's not an hourly or a daily type activity where you're going in and adding new networks again and again and again when you're in a production network. Typically your network is set up, right? And maybe you've got some adds or changes, but those aren't taking place on a daily or an hourly basis. Packet tracer activity that you'll be working, the distance vector technologies, right? So it talks about RIP v1 that it would broadcast out things. RIP v2, EIGRP. Now, RIP, they use the Bellman-Ford algorithm. That is not the same algorithm. And so here's why you need to be careful when you hear people say, oh, distance vector algorithms, they can fall, they're susceptible to count to infinity, which is a major issue with distance vector routing protocols that use the Bellman-Ford algorithm. EIGRP and IGRP, when it was used, they don't use Bellman-Ford. They use the diffusing update algorithm dual. And dual can guarantee loop freedom at all times. It will guarantee no loops in your network at all times. And that is a good thing. So be careful. Like I said, and that's why EIGRP is not a hybrid routing protocol. It is an advanced distance vector routing protocol, right? And so they'll give you some information here about RIP v1 and RIP v2. Definitely know this information, right? You see the 15 hop limit, 16 is infinity, and that is actually true for all of the versions of RIP. So the question you may be asking yourself is, well, why didn't they make it more than 15? Well, it's simply because RIP was a protocol, believe it or not. RIP was sort of born on the Unix operating system. It used to be called, on Unix, it was called GATE D. G-A-T-E-D was the name of the daemon that would run, but it was RIP, right? And that's where it was born. And in the early stages of the internet, RIP, and when I say early stages, I mean literally when there were like 5 or 6 universities trying to figure out, and the ARPANET, trying to figure out how this was going to work. RIP was one of the protocols that was being used, but it was very quickly discovered that RIP was not going to work, right? So it's got this hop count limit, and it was really overcome by events, right? You had OSPF, you had, and again, going way back, you had OSPF, and then BGP, there was EGP, and I don't mean to complicate things. So when we say EGP, Exterior Gateway Routing Protocols, there was an EGP whose name was EGP, but it's long gone. Excuse me. And it was overcome by BGP. And so RIP has kind of just always maintained this 15 hop count limit, because RIP is not a routing protocol that you're going to be running in a very large, complex network. It just isn't. It's for very small networks, and it works great in small networks, but it's just they just never updated it so that it would be more than 15 hops. And really, again, use case. If you've got 15 hops in your network, chances are you're not going to be using RIP. Chances are you're going to be running OSPF, or you're going to be running EIGRP. You're not going to be running RIP. Okay. Enhanced Interior Gateway Routing Protocol, EIGRP. And you can see the information here, right? I'm not going to read it. And there's that bounded triggered updates, right? It's bounded because it only sends it to the routers that need it. It's triggered because EIGRP is not broadcasting things out in terms of routing table information, right? It's the hello packets every 5 seconds, but it's not sending, oh, here's my whole routing table. Here's my whole routing table, right? I mean, that's just a waste of resources. That's overkill. It only sends things out when it's triggered to send things out. And we saw that. We saw updates, right? We go back to Wireshark. The update, I added in a new network, the 2222, and an update goes out. That is a triggered update, and it's bounded. It only goes to the routers that need to know about it. And that would be router 4, because that's the only other router speaking EIGRP right now. It converges very quickly. It supports multiple network layer protocols, and they call these protocol dependent modules. And here's what's kind of silly, right? It says, yeah, it supports multiple network layer protocols. So it'll say, oh yeah, we support AppleTalk, right? Who's running AppleTalk? Nobody. I don't even think Apple runs AppleTalk anymore, right? So yeah, that's great. But the protocols that we're concerned about is IPv4 and IPv6, right? Those are the two. Those are the ones that are being used. It'll say that it supports AppleTalk. It'll say that it supports Novell Networks. I can't even remember what it was called. Their network, but I mean, those aren't being used. It's IPv4, IPv6. That is what we're interested in. And EIGRP keeps a topology table, and we'll dig into that. All right, so there's a packet tracer activity here comparing RIP and EIGRP path selection. Remember, RIP only cares, and actually, let me drop back here real quickly, and this is a good point to make. What does RIP use as its metric? RIP uses hop count, and that's all it cares about. EIGRP is, and again, I'll sort of sarcastically accentuate this. It's an advanced distance vector routing protocol. So it takes into account by default bandwidth and delay, right? Which, I mean, let's be honest, that is way better than simply looking and saying, oh, what's the shortest amount of hops? So if PCA is trying to get to PCB and we're running RIP in here, what is RIP going to do? RIP is going to say, it's going to get to router A and it's going to say, yep, my best path is to take this 1.2 kilobits per second. That's 1,200 bytes per second. I mean, that is the Flintstones Stone Age type speed. Terrible. But it's 1.2 kilobits a second. It's 1.2, 1.2, and then we would make our way out here. RIP is going to go this way. Why? Exactly. 1 hop, 2 hop, 3 hops to get there. RIP looks up here and says 1, 2, 3, 4. No. RIP says that's bad. Too many hops, too many hops. Even though it's 100 megabits per second, 4 megabits, 100 megabits, which just by looking at this, right, you can quickly discern that the better route, the best route is up here. It's up on the top. But RIP won't see it like that. RIP says, how many hops? Right? That's all that RIP cares about. In fact, excuse me, this could be a 10 gig link. This could be a 10 gig link. That could be a 10 gig link. This could be a 10 gig link. And RIP will still say, go along the bottom. And again, we talk about use case, right? In small networks, RIP is great, right? A network like this, where it's sort of like this flat topology here, this is great, right? This is going to work great. And I could run RIP and that would be fine, right? But when I do something like this, is RIP the best choice here? If these are, let's say that's a T1, 1.544, and that's a T1, and this is a T1, and these are 10 gig, right? It's the same scenario that you're looking at over here to the left. Is that a good use case for RIP? No, absolutely not. And so these are the things as a network engineer you need to think about, that you need to take into consideration when you're deciding, what am I going to do from a routing perspective? Is it going to be static routes, right? If that's my setup, even if it's that, yeah, okay, maybe static works here. Am I going to be making a lot of changes? I don't know. Maybe static works here, right? It certainly works great like that, right? It's not that big of a deal, okay? But when you start to get into more advanced topologies, static routing gives way to the dynamic routing protocols, which then gives way to the conversation, do I run RIP here? Obviously not. Do I run EIGRP in here? Probably. You could run OSPF. OSPF uses the shortest path first algorithm, right? SPF, and it uses the bandwidth of the interface to come up with the cost or the metric, right? So again, both OSPF and EIGRP are better than RIP here, because RIP is always going to fail you here. It's going to choose the shortest path based off of hop count. All right, so hopefully that drove home the conversation and why you're seeing that. Now, chapter 5, the last thing we're going to talk about is link state dynamic routing. Now, I'm going to tell you right out of the gate that OSPF is probably one of the more complicated routing protocols that you'll work with, especially when you start to work with different types of topologies. And what I mean by that is OSPF is great. Again, if we have 2 or 3 routers and we're all connected to a switch and it's a multi-access segment, OSPF works like a piece of cake. And we have a designated router and we have a backup designated router, right? It's not that bad. But as the use cases start to change and you have different topologies, right, with different connectivity types, you'll start to find that OSPF can become very, very complicated very, very quickly. Whereas EIGRP is not as complicated with the different types of connectivity and different types of topologies. And so again, as we build through scaling networks here, we're going to be talking about that a lot, because again, it's all about, and the reason I drive the use case thing home is because a lot of learners ask, well, okay, well, what am I supposed to do? Why am I static routing, dynamic routing, EIGRP, OSPF? When do I use one versus the other? Why would I use one versus the other? It starts to become really overwhelming. And so that's why I like to sort of interject that use case point, is that a lot of times it comes down to the use case. The same thing, like I said, static routing versus dynamic routing, distance vector versus link state, right? Distance vector, RIP v2 versus EIGRP. It depends. And that's what makes a great network engineer better than a good network engineer, right? A great network engineer can recognize when use cases call for certain routing protocols. All right, so into the shortest path first protocols. We've got OSPF and ISIS, and for the purposes of this course, and ISIS is kind of starting to creep back into some of the Cisco Networking Academy materials. And it's starting to take on a larger role. I would love to see the Networking Academy start to add in some ISIS material. I think it's really great material to know. But for the purposes of our course, Networking 3, Scaling Networks, our focus is going to be solely on OSPF as the link state routing protocol we're working with. Now, as you can see here, it's Edgar-Dijkstra's shortest path first algorithm. So EIGRP uses dual, the diffusing update algorithm, which is a distance vector based algorithm. And OSPF, a link state routing protocol, uses SPF, the shortest path first algorithm. Now, the interesting thing is Dijkstra's shortest path first. I took a discrete mathematics course one time, long time ago, and it was actually in there. The SPF was in there, and how you calculate the shortest path first, because SPF, it's used in OSPF, right? I mean, open shortest path first. It's in the name. However, Dijkstra's algorithm has many, many more applications than link state routing protocols. It's used in many other types of applications. Like, what's the quickest way for me to get from Boston to New York, or from Miami to Los Angeles, right? Shortest path first. Okay, so it is a link state routing protocol. Those are the two that we're learning about here, but OSPF is really where the focus of this course is going to be on, not ISIS. And so here is how OSPF functions. It basically looks at the cost along the paths and determines what is the shortest route to get there. Again, hence the name, shortest path first. And each router is going to determine its topology, but that information within an area, within a single OSPF area, all of that information about all of the different links is going to be shared. And all of that information comes together in what we call a link state database. And let's take a look at that. Excuse me. Because OSPF is very easy, just like, again, very easy to configure, just like EIGRP is. It's very similar, right, when we're talking about basic configuration. And that's what we're interested in right now. Excuse me. So I'm on router 2. I'm going to go into global config. I'm going to say router OSPF, and I'm going to use 2 because I'm going to drive a point home here. And the point is, with EIGRP, the autonomous system number with EIGRP, which is what that number was when I said router EIGRP 1 or router EIGRP 99, the autonomous system number must match. With OSPF, this is a process ID. It does not have to match. And I'm going to show you that right now. And when I say it doesn't have to match, it doesn't have to match between the routers that are trying to form the adjacencies. So I'm going to say router OSPF2 on router 2. And then we're going to put in the network statement, right? Whoops. We're going to say network. And I'm going to use 10.2.4.0, 0.0.0.255. So right there, up until this point, is this not literally identical to what we just did with EIGRP? I said router EIGRP 1, and I put the network statement in with the wildcard mask. It's exactly the same with OSPF. We've got one difference here. Now, this is, again, OSPF is definitely more complicated than EIGRP when you get into different advanced use cases. So I've got my network state, but I have to put the area, right? And we're interested in area 0, a conversation that's going to be held off until we get into later chapters. So I say router OSPF2, I throw my network statement in, and I say that interface, or I should say any interface on this router in that range is in area 0. And we have a single interface in that range. So let's see, what do we think Wireshark is saying right now? In fact, is it running? I stopped it. So let's kick Wireshark off and we'll say continue without saving. And here's what we're going to see on router 2. Oops, there, let me stop it real quick here. And there it is. Take a look. It's the exact same thing. It starts the OSPF process on the interface that falls within that network statement range. And the process, OSPF, does just what EIGRP does. It's sending out multicast on a multi-access segment here, right? We're sending out multicast packets to 224.0.0.5. And I'm basically saying, hey, I'm router 2. I'm over here. I speak OSPF. If anybody else is OSPF capable, I would love to form an adjacency with you. And you can see here, just like EIGRP had the parameters, OSPF has a header, right, with information. It's a hello packet with additional information, and then the link layer block, but we're going to leave that out. That's not important. But here it is saying, here's my network mask. My router priority is 1. DR, BDR, right? It's looking for the designated router and the backup designated router. And we'll get into that a little bit later. But again, you can see it's very similar to what EIGRP did. We configured it almost identically. So let's go on to router 4 and let's see what happens. We'll step over here to router 4 and we'll come in and we'll say, we'll go into global config, global config, and we're going to say router OSPF 4. Right? Let's add a network statement in here. 10.2.4.0.0.0.255 area 0. Now, let me kick off the capture over here because now we're going to see what they call link state packets, or LSPs. And these are going to be communicated back and forth. And oh, I love it. Look at that. Nice color coding here. And that's Wireshark doing that for me by default. So take a look. Once router 2 and router 4 discover each other, we've got database description packets, right? Lots of database description packets going back and forth. We've got a link state request. And this is all about building the link state database, right? We've got link state updates that are going back and forth. And again, take a look. I'm running EIGRP and OSPF on the same routers. You can do that, right? If you go on to your CCNP level studies, you'll talk about what happens when you do things like that. And we'll talk about it a little here, but not as in depth. So again, look at that. I've got a neighbor. So do show IP OSPF neighbor. And there it is. Right? Let's take it one step further. Router 4 connected to 5, 10, 11. So let's do this. Let's go to router 5. And let me make sure I don't have show run section router OSPF. I'm making sure I don't have a section OSPF configuration already here. All right, so on router 5, I'm going to come in here and I'm going to say router OSPF 5, right? Remember, it's a process ID. It doesn't have to match. And then we're going to throw a network statement here, 10.4.5.0.0.0.255 area 0, right? Now, I need to do the same thing on router 4, correct? Because this is a different interface. Whoops, 10.4.5.0.0.0.255 area 0. And I think we stopped our Wireshark. Let's kick Wireshark back off. And let's see what happens here when I enable that. All right, we've got link state updates going back, right? You can see router 2, and oops, let me stop here. You can see router 4 sending a link state update. We've got router 5 sending a link state update. And if I transition back to the routers here, let me make sure I've got connectivity. Sometimes it takes a few seconds, 10.5.5. All right, we've got connectivity. So do show IP OSPF neighbor. And you can see, and it just popped up there, that we're in the two-way state. So again, sometimes on some of these routers, it'll take a little longer. We'll come over here to router 5. Do show IP OSPF. And there we go. And we went from loading to full. Because it's got to transition through the different states of the OSPF state machine, right? So, whoops, I did not want that. I'm sorry. So let's go ahead and say in, and we'll say show IP OSPF neighbor. And there we go. I'm fully adjacent. I see the other router is the backup designated router, and that's the interface out which I have this adjacency. So now let's go one more router. Let's go to router 10, and let me make sure that it was 5 and then 10. Okay, it's 5 and then 10. So over here on router 10, I'll go into privilege exec, into global config, router OSPF 10. The process ID does not have to match. And I'm going to say network 10.5.10.10 and 0.0.0.255. Sorry, I'm thinking as to whether or not I've got this configured properly here. Let me say do show IP interface brief. Yeah, so I don't have, let's get an interface gigabit Ethernet 00.510. So I need to configure that interface real quick. So incap.1q510 and IP address. And that encapsulation command, again, you can ignore sort of what I'm doing here on the interfaces when you see these encap commands, because it's a little advanced way to set my lab up that makes it easy for me so that every router can speak to every other router if I wanted it to. IP address, and we're doing 10.5.10.10, and this is a 24. And we should be good to go. And let's say do ping 10.5.10.5. And let's repeat that a few times here. Should take it. Okay, good. So we've got connectivity. So our configuration is set up here under router OSPF 10, right? If I say do show run section router OSPF 10, that's my configuration, right? So now let's drop back over here to router 5. And let's go ahead and say, get into global config, router OSPF 5, and let me add the network statement in so that I can start the OSPF process on the interface between router 5 and router 10 on router 5 now. And I say 10.5.10.0, oh, sorry, not 255, 0.0.0.255, and we'll put that in area 0. Now, are we capturing any of this activity here? Let's capture it and see what happens here. Say continue without saving. I'm going to come over here, hit enter. We're going to drop and take a look at that. And this is what I love about Wireshark. It is going to give you the nitty-gritty of what's going on. You're going to get more information out of Wireshark than you would anything else. And so you can see that between router 5 and router 10, right, and router 4 is sending out link state updates, and this right here, that picture right there, should be driving home the point to you that every single router running OSPF is doing something here, right? They're sending link state updates out. Router 4, router 2, well, we don't see router 2 listed here. There's router 2 down here, right? So, but when you look at what's happening here, every single router is talking to either the designated router, and we'll get into that a little bit later. That's this multicast address here, 224.0.0.5. It refers to the designated router, or to an individual router, right, with updates. And it's going back and forth. So now I'm going to do something here on router 10. On router 10, there should be a loopback address, and there probably isn't, but let me go ahead and set that up. IP address 10.10.10.10, 255. And what am I missing? Oh, it's got a typo there, 255. So we have this interface here, right? This loopback 0. And over here on router 2, if I was to say, show IP route OSPF. Whoops, show IP route OSPF. You can see that I only know about those two networks via OSPF. But I want to get to the 10.10.10.10, this new network over here on router 10 that we just created. Well, I'm going to advertise it, right? Or I'm going to start, and let me correct, I'm going to start the OSPF process on that interface, right? Which is then going to generate a link state update. And so let's go ahead and do that. If I were to go into router OSPF 10, and I was to say network 10.10.10.10 0.0.0.0.0, right? Just like we did with the 2.2.2.2 and EIGRP. It's a host route, so we put the full IP address in the quad zeros. And then I say area 0. Now, let's see what happens here in Wireshark. Sometimes I say packet tracer. It's Wireshark. I mean Wireshark. So I'm going to go ahead and I'm going to advertise that out, and we're going to jump back and take a look. So we've got all kinds of cool updates going on here. Router 10 sends a link state update to the DR, right? And then router 5 sends an update to its DR. 4 sends an update to its DR. And then you've got acknowledgement, 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 right? So this is the power of a dynamic routing protocol. I make the change one time, right? I add one command in here into the OSPF configuration. And how many routers away are we here? So we're on router 10, right? And this is where we have that 10 network. An update followed by an update followed by an update. Let's come over to router 2 now. Let's come over to router 2. And on router 2, let's say show IP route OSPF. Do you see anything of interest here? And I've just highlighted it. And there it is, right? That is the power of the dynamic routing protocol. Think about if I had to do this statically. I'd have to put 2 static routes on every router. One on each of the routers saying, here's how you get to the 10, 10, 10, 10. Here's how you get to the 10, 10, 10, 10. Here's how you get to the 10, 10. Going hop by hop by hop, adding static routes on. A new network segment gets added to router 10, this 10, 10, 10, 10, right? It's a loopback. It's a logical virtual interface, right? And we're pretending it's a network segment in our conversation. But again, the point should be, I literally put a single line of code on router 10. And router 5 knows about it. In fact, let's step back. Does router 5 know about it? Do show IP route OSPF. Yeah, there's the 10, 10, 10, 10. And then router 5 sent an update over here to router 4. Hey, I know about show IP route OSPF. Hey, I know how to get to the 10, 10, 10, 10. Because look at the next hop for router 4. 4 says I just go to 5. I look at 5. 5 says, yeah, no, I just go to router 10. That's how you get there. And the shortest path first algorithm is calculating the cost, right? And coming up with the best way to get there. And you can see here, router 4 says go to router 5. And what do you think router 2 says? Yeah, go to router 4. And so this is sort of the map, the database that's getting built by OSPF. And real briefly, if I said show IP OSPF database, I'm trying to think of what to show you here. We'll just show you the whole database. Here is the OSPF database, right? Now, what you see in here is not really relevant at this point in the conversation. It will be when we dive into OSPF. However, that is, when you hear about this LSDB, the OSPF link state database, there it is. That's what it is right there. That is the database that OSPF learns and constructs in order to make its decisions as to where it's going to route its traffic. All right, excuse me. And it's all based off the cost. Again, we saw LSPs, we saw those link state packets, right? We saw all kinds of stuff. We saw database descriptors, we saw updates, we saw link state requests. And what do we got here? Yeah, learns its own, sort of similar to the cold start, right? It knows about its own directly connected networks. And then there's the hello packets that we saw, right? Hey, I speak OSPF. Does anybody else out here speak OSPF? Building the link state packet, right? It's going to send out all the routing information it knows about. And now here's the key takeaway with a link state routing protocol like OSPF. When we talk about convergence, every router must have the exact same link state database, or else OSPF is not converged. With EIGRP, did it matter that router 10 had the exact same copy of stuff that router 2 had? No, it doesn't. They're going to make independent decisions as to whether or not they're converged compared with OSPF. With OSPF, it's all or nothing. Every router in the OSPF routing domain has to have the same copy of the link state database for that area. And the flooding, right? We saw the flooding, right? All those black and was it yellow? Yeah, there's your flooding, right? And we saw, and actually it's gone. I didn't save it. But the one that had tons of black and yellow lines for OSPF, that was a ton of flooding. All right. And then that's where they build the map. They come up with the different costs, right? The routers come up with a different cost to reach different networks based off of what they're being told from other networks in the same area. And you can read through this. This is how the tree gets built. It's actually far more complicated than this mathematically, but this is a great overview as to how the routing table comes together. Okay, the advantages, let me see here. Yeah, it's definitely a higher, and this is actually a key point, hierarchical design. In EIGRP, the hierarchy is arbitrary. I can have, I could create a topology in EIGRP that literally look like this. Router connected to this router, maybe it's over here, and then there's a router over here, and then this guy's connected here, and then these two guys connect down here, and this guy connects over here, and then this guy connects out here, and he connects to two other routers here. Now, again, sort of illustrating the point by being a little absurd, but with EIGRP, the hierarchy, right, is arbitrary. So, excuse me, I could lay all of this out like this. There's no areas in EIGRP that I have to be cognizant of or aware of. It doesn't matter to me. I can just throw everything together just like this, and EIGRP is going to work fine. With OSPF, remember I stressed that area 0, right? So these routers, right, if they're connected like this, whoops, and I'll draw that down there, they all need to be in area 0. If they're in the same area, right? And here's what the hierarchy talks about. And we talk about multiple area OSPF or multi-area OSPF. And we'll get into that later, but here's what they mean about hierarchy. Any area, and you remember when I ran the command, network, whatever, area 0. That means that that interface for that router is in area 0, right? So all of these would be in area 0. Now, let's say that I've got a router here. You notice I drew it on the boundary of area 0. And those interfaces are in area 0. All the red's area 0. But that router connects up to another area. And hopefully, is that green? Okay. This router connects up to another area. And maybe this area over here is area 51, of course, right? And there's a router in here. And his interface is in area 51. And that interface on that router, this interface is area 51. Because the area assignment can be router wide, right? I can do it so that every interface is in area 0, but I can also pick and choose. We'll talk about why you would want to do this. And so I could say that that's area 51, right? I'll put a 51 in here. And so the hierarchy is any non-area 0 area must connect to area 0. And so the two terms I like to use should be a star, right? So if this is area 0, every non-area area must connect to area 0. And it's also referred to as a hub and spoke. Whoops. Oh, that's terrible. Sorry about that. It's referred to as a hub and spoke. So here's my hub, and then I've got all these spokes. And again, it looks just like the star topology that I drew over here. So these are two ways that it's referred to, as a star and as a hub and spoke. Because area 0 is your hub. All non-area zeros must connect to area 0. EIGRP, there are no areas. It doesn't matter. You just plug everything in. As long as it's in the same autonomous system, you're fine, right? All right, so let me step through here. And right on cue, I did not know this was the next slide, but here we go. The disadvantage, right, is that you've got multi-area setups. It's a very strict layer, a very strict 2-layer hierarchy. You've got area 0, and you have all other non-area 0 areas. In EIGRP, hierarchy doesn't exist, right? And they talk a little bit about ISIS here, right? Again, they just kind of get your feet wet, let you know that there is another link state routing protocol out there. And again, you won't see it in the curriculum today, the Networking Academy curriculum. You don't even see it when you get to the CCIE level. ISIS isn't there, but I believe it is making a comeback. And the fact that they're starting to mention it here at the CCNA level, I think you're going to start to see it trickle into other curriculum, the CCNP courses probably, because ISIS is extremely powerful. It's used by service providers, right? Verizon, Hurricane Electric, Level 3, right? The huge service provider, AT&T, that are out there, they're using ISIS as their internal gateway protocol. All right, chapter summary, pretty brief, right? And I will let you work through that. I'm going to go ahead and pause now so I can rotate the slide deck out, because now we're going to jump into EIGRP, chapter number 6. So let's go ahead and pause, and I will be right back.